Okay guys, in this video we are going to be discussing calorimetry, which is an experimental technique for measuring heat, and we're going to look at two types of calorimetry. I'm going to go ahead and skip this slide and we'll just jump into the two types. So the first type of calorimetry is solution calorimetry. As the name suggests, it's useful for measuring the heat of reaction associated with the chemical reaction taking place in a solution, typically an aqueous solution. And in the general chemistry laboratory, we usually demonstrate solution calorimetry using what's called a coffee cup calorimeter, which you can see here on the left. It consists of two coffee cups that provide insulation between the chemical reaction mixture and the surroundings in the laboratory. And so the idea here is that you will mix two liquids, an acid and a base, for example, or perhaps you will dissolve some solute in water, and that dissolution process may produce heat, or it may absorb heat. And then you will monitor the temperature change of the water. Okay? And by measuring the temperature change, you can calculate the heat associated with the chemical reaction taking place in the calorimeter. This is a diagram of a more sophisticated solution calorimeter with some computer control, and a fancy stirrer and a precision thermometer, and it can be used to obtain very precise and accurate heats associated with chemical reactions. Regardless of whether you're using an inexpensive calorimeter or an expensive calorimeter, the approach to how to get the heat of the reaction is the same. Because the reaction mixture is insulated from the surroundings, we can take the heat of the reaction plus the heat of the calorimeter to be equal to 0. So, for example, suppose that you have a reaction where heat is being produced. That heat will in turn be absorbed by the calorimeter itself. And so, because no heat can escape, that's the only place for that heat to go. So the sum of the two heats must add up to 0. We can expand the heat associated with the calorimeter in terms of the heat capacity of the calorimeter and the measured change in temperature. So if you know or have previously calibrated your calorimeter such that you know the heat capacity of the calorimeter, you can then measure the delta T for your chemical reaction and use this equation to find the heat of the reaction. In the second type of calorimetry, which is called bomb calorimetry, bomb calorimetry is often used to study gaseous reactions, in particular combustion reactions. And so in the instrument you see here on the left, you see this steel canister. This is called the bomb. It's a very rigid, strong canister, and inside there's a little sample cup where you can put different types of fuel. Organic compounds or even foods can go in here, and then you can measure the heat associated with the combustion reaction. So you would then pump it full of oxygen, excess oxygen. You seal it, it's sealed up. You pump in oxygen, and then there's two electric leads coming out of the bomb. You can fire the bomb, and that ignites the material inside the bomb calorimeter. And then what you do is you measure the temperature change of the calorimeter. This is a water bath that surrounds the bomb vessel. You monitor that temperature change, and then using this same equation here, you can calculate the heat of the combustion reaction. You do need to know the heat capacity of the calorimeter before you can do the calculation. So you have to calibrate your calorimeter before you can use this equation. You need to figure out what its heat capacity is. Well, we're going to work a couple of example problems. We've worked this one already. as well as this one. This one is identical to the last problem. And so here is where the calorimetry problems begin on slide 251. This is going to be an example of solution calorimetry. So we've got an acid and a base, and they are being mixed together. Notice that we've got 50 milliliters of the acid is being combined with 50 milliliters of the base. Initially, the reaction mixture is at 22 degrees Celsius, and then as the reaction proceeds, we find that the temperature reaches a maximum of 28.9 degrees Celsius. And from this data, they want us to determine the heat produced by the neutralization reaction. We need a little bit more information. They say assume that the density of the reaction mixture is approximately 1 gram per milliliter, and that the specific heat of the water is 4.194 joules per gram. We are to basically assume that the heat of the reaction is essentially absorbed by the water in the solution. And so since we have a solution with a density of 1 gram per milliliter, and we've got 100 milliliters of solution when we add these two 50 milliliters together, we've got about 100 grams of water. We know its specific heat, so we can take this to be the calibration constant, or the heat capacity for the calorimeter. So here's how the problem works. I've already got it written out, so I'm just going to reveal the different lines as we go through the problem. Here's the basic equation. The heat of the reaction is counterbalanced by the heat absorbed by the calorimeter. So the two add up to 0. We're going to expand the heat of the calorimeter in terms of the specific heat of the water that's in the calorimeter. So here's the mass of the water, the specific heat of the water, and then this is the measured delta T. Okay, so we can use this equation, since we know all of these quantities, we can use this equation to find the heat of the reaction just by rearranging the equation a little bit. And then we plug in our numbers. So plug in the 100 grams for the water, the stated specific heat, and then this is the delta T for this process. And so then we have calculated here, calculated the heat in units of kilojoules, minus 2.89 kilojoules in this case. The next problem is a bomb calorimetry problem, and they make it slightly more complicated, as we'll see here. So we've got 3 grams of glucose is being burned inside the bomb calorimeter. The temperature change of the calorimeter is measured. It goes from 23.8 degrees Celsius initially to 35.6 degrees Celsius. The calorimeter contains 775 grams of water, and the bomb calorimeter itself, not including the water, has a heat capacity of 893 joules per degree Celsius. And so this is where the complication arises. We need to add a third term here to the calorimetry equation. Here, the heat of the reaction will be equal to whatever heat goes into the water plus whatever heat goes into the calorimeter itself. So this would be the metal part of the bomb vessel. And they give us the heat capacity of that. So we're going to expand these two terms. Here I've just rearranged it. Solve for the heat of the reaction. It's going to be minus the heat of the water plus the heat of the calorimeter. I expand the heat of the water. That's the mass of the water times the specific heat times the delta T of the water. The heat of the calorimeter is expanded as the heat capacity of the calorimeter times delta T. Okay. All of these quantities are known. We just look up the specific heat of the water, plug those in. So here's the mass of the water, the specific heat of water. This is the heat capacity of the calorimeter. And then this is the temperature difference that's measured during the experiment. Plug all those numbers into your calculator, and you get a value of minus 48.8 kilojoules coming out. And so this is an example of how bomb calorimetry is used to measure the heat of combustion for glucose. I will point out In the physical chemistry laboratory, which is one of the upper division courses, we study bomb calorimetry, and we use in that experiment we use the bomb calorimeter to determine the combustion energy of a glucose of a Smarties candy, and then we compare that information with the nutritional facts of Smarties candy to calculate, or to, that lists the calories, the food calories per serving. And in fact, that's one of the applications of bomb calorimetry. So those nutritional facts information you see on all of your food packaging, the calories can be determined by the technique of bomb calorimetry very accurately, I might add. And so anyway, that's an application of calorimetry in everyday life. So with that, I am going to end this video, and we will talk about the first law of thermodynamics in the next one.